Hi everybody, this is Michele Killa speaking. I'm from Qualcomm Ireland, and thanks for attending the meeting and the presentation of my paper, which I made with my co-worker Leonardo Goppi. So we both work in Qualcomm, and I'm a digital engineer, and I work on the Sensor Snapdragon controller. Today I'm going to talk about this paper, which essentially has a piece of it in it, and the title is Clock Controller Unit Design Metrics, Area Power, Software Flexibility, and Congestion Impact at System Level. So here is the agenda. So first I'm going to talk about the idea and the problem statement behind this paper. And then I'll go through the solution that we have adopted and the subsystem under test and the three clock controller design strategies that we developed. And then I'm going to comment the results we got with some conclusions. So let's start with the problem statement. So as you know, all the CPUs are generally sequential circuits which are governed by a clock. And essentially nowadays the semiconductor companies and industries are trying to develop CPUs, high-speed CPUs with high clock frequencies in order anyway to make the signal processes faster, but at the same time they want also to support multifunctions because for instance, if you look at the current smartphones, right, so all these devices can do a lot of things, even like when you have them in your pocket. But anyway, they still do something, right? In the meantime, for instance, counting the steps. So, of course, anyway, this such amount of signal capability and the faster clock don't bring benefits anyway on the mobile devices, especially anyway for the batteries, because of course, as we know, all these mobile devices depends on battery life. And of course, if we leave like the circuit to consume a lot of power, which is anyway strictly related to the clock distribution, the clock speed, and also anyway on the amount of things and signal processes that the chip is doing at that time, the battery's life anyway will be reduced. So architects, what they have to do in the last few decades is to kind of restructure the system. And essentially, in the past, what we were used to have, it was like a system with one single clock supporting anyway all the functions at the same time. But essentially, this one anyway doesn't bring too much benefit from designer's point of view because nowadays there are and they exist some low power techniques that can be applied to the system in order to reduce power. So the solution that the architects adopted is to migrate from a single clock system to a multi-core and multi-clock system, where essentially what we can see right on the right hand side, they split the system in different and smaller blocks, each of them supporting a particular function. So in this case, when a function is no longer needed, the designers can apply the power gating technique, where essentially you just cut off the power on that subsystem. For instance, in this case, if the video subsystem, right, where we have our smartphone in our pocket, right, the video doesn't need to work, right, so there's any video activity on the chip, they can shut off anyway the power for the video subsystem. And this one anyway brings a lot of benefit from power saving, both on the dynamic side and the leakage side. But at the same time, the clocks also has a big impact anyway on the power dissipation and the power dynamic, especially consumption. And this is because, of course, the frequency, the power dynamic depends on the frequency. So what they did essentially, instead of having one single clock for the system, they prefer to have multi-clocks, right, to clock all the resources inside each subsystem. And this allowed the designers to implement some techniques such as clock gating, which is part and essential of this paper, where essentially you just get the clock when it's not needed. Having multi-clocks also allows the software to control the frequencies of those clocks to reduce the frequency when, of course, the signal processing is reduced. And depending on the use case, the frequency can be bumped up or they can also anyway reduce. And at the same time, having multi-clocks, you can also anyway make all the cores inside each subsystem, for instance here, asynchronous each other, means that of course you need to make sure that you have synchronizers between your cores, but of course the clocks can be asynchronous. This is also anyway a good advantage for a physical design team, because when they build the clock tree structure around the SoC. They have more flexibility anyway, and they don't need to balance all the clock tree in order to have on all the flops, right, the front edges of the clock matching. Just to give you some numbers, for a high complex subsystem, we can have plus 80 clocks generated, which is a really high number. And of course, if we can implement techniques like clock gating or dynamic frequency scaling, it brings lots of benefit in terms of power dissipation. Let's talk now about what we did in this paper and the solution that you adopted. So essentially what we did, we picked one of the subsystem, which is the system where I work on, is the sensor subsystem of the Snapdragon 855 platform. And this subsystem has its own clock controller unit. And we tried to restructure the clock controller in order to maximize the dynamic frequency scaling and the clock gating. But at the same time, we try also to make it and actually make the physical design life easier when building the clock tree. So essentially, and also anyway, one thing that we have to consider is the fact that the tree version of the clock controller that we developed, they generate the same number of clocks with the same frequency. It's just a matter of how we generate and actually what is behind the clock generation itself. So the work that we perform is essentially the following. So here we can see three versions of the same clock controller unit. We have the low optimized clock controller unit, the middle optimized clock controller unit, and the high optimized clock controller unit. And we essentially instantiated these three versions in the same subsystem RTL, which is the sensor subsystem. After that, along with the timing constraints related to the fact that we make clocks synchronous or asynchronous to each other, we run synthesis. So all these two are inputs to the synthesis tool. We use the sign compiler, and then we extract data, area, power, and also we use the design vision to check and get a first flavor of the clock tree routing in the chip. But also at the same time, also software flexibility. That's why clock controller unit metrics, area, software flexibility, congestion, and area impact, power impact. So let's go through the clock controller design strategies. So, well, before going there, let's talk about the basic blocks that every clock controller unit generally has. We have a PLL, which is generally a PLL phase locked loop cell where it's used to generate different types of frequencies on the output of it, and generally those ones are controlled through software, and the output clock depends on the phase of the input clock. Another thing, another block, basic block important, is the clock multiplexer. So essentially this block is widely used to perform the DFS, the dynamic frequency scaling. So essentially it gets as input different clocks with different frequencies or different clock requirements. They can be asynchronous also. And based on software selection, they propagate that clock through the output of these MOOCs. Of course, this kind of MOOCs is not like a general multiplexer, because we need to guarantee that whenever you switch between two inputs, there's no any glitch propagation on the output of it. Other blocks are the divider, which are also widely used to perform dynamic frequency scaling, and generally are controlled through software. So software can decide which is the divider value of the clock output. And then the clock gating cell, which is used to perform the clock gating, and generally it's a simple cell made by a latch and an AND gate. And it's used anyway to get the clock when it's not needed. And generally it's controlled through software, but the hardware should also have the mechanism to get the clock when it's needed, because sometimes software prefer always like hardware solutions for getting the clock. This one is the first type of clock controller design that I'm going to present, is the low optimized one. So I can't share anyway too much information about the clock controller unit inside the sensor core for PCI policies, but anyway, this one is a good representation of it. Here we can see there are 11 clocks generated on the right side, and there is one clock SMUX here, which gets us input two RTO clocks from the ring oscillators that can be sit outside the SoC, and two PLLs, which can be sit in digital PLLs, which are inside the SoC. This clock MUX generates different clock branches, and each clock branch, which are this one here, is driven by a divider. So software can switch between these inputs here and also program the divider in order to get the target frequency required. Regarding this, why this strategy anyway is low. First of all, we have only one single source. The one clock MUX means that from DFS perspective, we have a pure DFS. So software has not too much flexibility of choosing which clock needs to be picked, because whenever they switch or they use the RCO, these RCO clock impact all the branches on the right-hand side. At the same time, one constraint for implementation team is that we consider all the clocks synchronous each other. So when the clock tree is built, it makes sure that all the branches are balanced in the SoC. So we expect an high buffer insertion in a way to make sure that all the front edges on the flops match. Something different is on the mid-optimized clock controller unit, where essentially we kept the same pool DFS, so we have still one clock MUX here on the left-hand side, but we make the clock branches asynchronous each other. Means that at the physical implementation level, they don't need to make these clocks here synchronous with them. So of course they have much more flexibility, and they can play anyway with these clocks as they like, essentially. So and this anyway brings a lot of benefit, because of course the clock tree, it's more, the constraints on the clock tree is lighter, and there's gonna be a less buffer insertion. Something different is on the optimized design, where essentially every clock group has its own CMUX. So in this case, we have the highest DFS as possible, because of course, whenever you switch the first clock MUX, two inputs of the first clock MUX, it doesn't impact the other one. So software has kind of independent control of each clock branch. And at the same time, all these clock domains are, all these clocks are split in asynchronous groups. And one thing anyway that to say is that from our analysis, what we did, all these clock MUXes are driven by the same RCO and PLLs. Essentially, these ones are shared between all of them. This one is a kind of summary and expectation of the result that we could get. So essentially, in the low optimized ECU, as I mentioned, we have all the clocks synchronous each other, which means we expect they are actually tight timing constraints for implementation. Since there is only one CMUX for the DFS, we expect one high fan out, because of course now this CMUX should clock and is the source for all the clocks of the subsystem. And essentially, since the timing constraints are tight, we expect an high buffer insertion. Regarding the dynamic power, the DFS is pretty poor. On the mid-op CCU, we have more relaxed timing constraints, because we made all the clock branches asynchronous each other, and but at the same time we still have one single clock MUX which drives all the clocks, so we expect an high fan out. And regarding the buffer insertion, because of the first two, right? This one we expect a moderate buffer insertion. On the dynamic power, the DFS is still poor, because of course we have only one clock multiplexer as source. On the IOPT, all these things get improved, and of course we're going to have all the clocks asynchronous, so we expect a reduction in the buffer insertion, and also anyway the fan out of each anyway is reduced, because of course we have one dedicated clock multiplexer per clock branch. And the DFS is higher, of course, because we have a dedicated CMUX per clock branch. Now, let's talk about the results. So this one is the methodology that we adopted to gather all these numbers. So essentially, we analyze the area and we get these numbers from the sign compiler tool. We analyze the combo and the non-combinational area and most of all the buffer insertion, which is something that we would like to see. Then regarding power, also we use the sign compiler to get these numbers, and we use the predefined models provided by the tool itself, and we estimate the leakage and the dynamic power. Regarding software flexibility, this one can be deducted from the design itself. So we can see that on the I-optimized CCU unit, we have the maximum DFS. And regarding the congestion, we use the SignVisio tool to extract the first flavor of the clock tree and the floor plan of this system down to the 6th level of connection. So let's look at the area comparison. So this graph here essentially show a comparison between mid-opt versus low-opt impact at system level. Then we have I-opt versus mid-opt at system level, of course, and then I-opt versus low-opt. Now, what we can see here is that in all the three cases, essentially the numbers here are pretty low because, of course, the area occupied by the clock controller unit in the system is pretty small. But essentially, what it's important to see is the fact that when we move to one single domain where all the clocks are synchronous each other to a clock branches are synchronous each other, the buffer insertion decrease. And we can see that if we compare the mid-opt versus the low-opt and the I-opt versus the low-opt, where we apply this feature, the buffer insertion decreased. Regarding the total area, the impact, as I mentioned, it's pretty negligible. And regarding the combo area here, we can see some discrepancies, but those ones are mainly due to the fact that to guarantee this type of design features, we have to implement some small RTL changes, and but of course, anyway, the clocks and the frequencies are always anyway the type of clocks and the frequencies are always met. Regarding the power consumption instead, what we can see here is the fact that if we compare the mid-opt versus the low-opt, the switching power decreased a lot, is 20% less. So this is because, of course, on the clock tree path, all the clocks now are synchronous each other, while in the low-optimized, the clocks are all sync. Something different anyway can be seen on the I-opt versus the mid-opt, and the reason is because, of course, now we had implement a different clock multiplexer, which of course are blocks that are gets as input a clock who has of course a switching activity equal to 2, because of course clocks is the highest, is one of the wires that toggles mostly right in the integrated circuit. So that's anyway why we've seen this such amount of increase in the switching power and also on the total power. But anyway, what is important to see is that if we compare the I-opt versus the low-opt, the impact of the power is pretty negligible. So, and actually the switching power decreased. So in this case, of course, we have the highest DFS, right? But and the switching power actually decreased. The internal power increased a bit, but it's due to the fact that I-opt has more cells instantiated. But essentially, overall, the impact is almost the same. Regarding the routing congestion, these ones are the snapshots that we got from the SignVisio tool. So on the left-hand side, we can see the fan out of the clock controller unit for the mid and low optimized design, because of course in both of the cases we have only one single source. And here, essentially this part here is where all the clocks get generated. And if you can see all the clocks, and which are the yellow part, they hit all the edges of the subsystem here, which is confined in this shade here. But in the I-opt, right, what you can see is that here we have highlighted with different colors the fan out of each clock multiplexer that we've instantiated. And essentially, in this case here, what the physical design team, what they can do, they can move this clock multiplexer closer to the destination point of the clocks, because of course generally all the clocks synchronize each other. They generally go to the same core, which require the clock synchronous. So of course here you have much more flexibility in routing the clock around the subsystem. Let's go about the conclusion. So here anyway, just a summary about what I already explained in the during the result presentation. So a multi-clock domain approach leads to a switching power saving and a buffer insertion reduction. So when we go through mid to high opt, when we go actually to low to mid or high optimized, higher software flexibility is responsible to increase the switching power, as we've seen, while the internal power effect is negligible. The total area variation is minimal and negligible because, of course, the clock controller unit, as I mentioned, it's as I said, it's the area occupied. It's pretty small. And routing congestion analysis show that the multi-clock domain approach gives backend stage higher flexibility when building the clock tree. Now, there are like few things that I would like to comment is the fact that mainly on the power numbers. So of course, all these numbers anyway have been gathered using DC tool and predefined models, right, of it. But of course, what we know is that the dynamic power depends strictly to the switching activity of all the wires. Now, in this type of analysis, we use predefined model, right, which model the switching activity of all the wires. But of course, this one doesn't reflect the real reality. So essentially, what in the real world, right, when there is a real power analysis, the designer they usually run simulations, right, on the RTL, and they get the switching activity of all the wires. Using it, they perform the power analysis. So one good thing that could be done right in future is to run anyway real use cases on the RTL, get the switching activity of all the wires, and then analyze the dynamic power using those numbers. So in this way, of course, we can get much more real number which are closer to the reality. And of course, at the same time, what we can do, we can also run simulation on the physical design netlist, which has also anyway is much more closer to the reality. And this is also anyway has all the information regarding all the buffer insertion that has been inserted, which of course is not present during in the RTL. That's everything, and thank you for watching.